Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we are going to discuss about the rate levels that is constructed within a rate structure. So this rate structure provides different types of levels. We will discuss about each level, where these levels are implemented and what is the area test to be tested on these rate levels, and depending on which factors we choose a rate level for a particular system on structure. For a rate structure, we know that mirroring provides reliability, but it is then expensive. And as well as striping provides high data transfer rates, but it does not improve the reliability. So, many schemes have been proposed to greatly reduce the redundant, lower the cost, and giving us a combination of striping with parity bits. Now these schemes are often classified according to the levels on rate or known as rate levels. So this provides a different trade-off in terms of cost and performance. And for our discussion of every rate level, we are taking 4 disks that are worth of storing the data, and the extra disk we will use will store the redundant information for correcting about the failures. So the first level is the rate level 0. RAID level 0 provides striping of the data or blocks outside the disk, but it does not provide any kind of reliability. So first we will know that how to write this RAID level 0 disk. So here we can see that only 4 disks are needed to stripe off all the data between them, but no redundancy or no error checking method is used in that type of RAID level 0. Here it provides high performance and data transfer rate, but it does not improve the reliability. So we will introduce our next type of RAID level, that is RAID level 1. RAID level 1 provides reliability by providing mirroring of the disk from one image to another image. So this type of RAID level 1 improves the reliability in terms of performance, but it is then very expensive because twice the numbers of the disk will be needed to mirror all the data. Here we can see that the 4 disks are both storing the data, and these disks are used for the mirroring. So exact number of the disks that is storing the data will be copied to the number of the disks that is to be mirrored. But it provides that it is very expensive, so we do not use that is in the operating systems very wisely. Our next level is a RAID level 1. RAID level 1 uses the memory system of error coding checking scheme. In this memory system of error coding checking scheme, the memory system checks for any error within a single bit that will check for every byte of the data or block within a disk. So that bit is known as a parity bit. So with a byte of every associated block, we attach a parity bit that will then check to any error type of computing inside that particular block. Say for every bytes in a disk, we calculate the number of bits in that byte that is set to 1. It is even or odd. For even the parity bit is 0, and for odd the parity bit is 1. So whenever this stored parity bit is already in the block, now we check by the memory system that after computation, if a disk or a particular bit in that disk is damaged, like by damaging one from 0 or from 0 to 1 in the parity bit, then we can signify that the disk has been corrupted. So if the computed parity and the stored parity does not match, then we can specifically say that there is a type of error in that particular bit inside that byte on that disk. So in this way, memory system uses the parity bit as an error coding checking scheme to detect these errors and correct the errors as possible. This idea of error coding checking scheme can be directly applied to the disk striping over the blocks on that particular disk. Say for the example, if it is containing a byte that is 8 bits, so we stored the first bit of this byte in the disk 1, the second bit in the first sector of the disk 2, third bit is in the first sector of disk 3, as well as the 8th bit in the first sector of disk 8. Now the parity bit is stored in first sector of any other bit. So whenever we are striping of the data, so we can changing in the parity bit indicates that any of these bits has changed. And as all the bits are stored in different disk, then we can easily signify that which bits has caused the damage, and we can then the disk replace or repair the disk as per possible. So after the damage has happened, then we can say from the other bits of that byte from other disk, along with the error correction coding checking bit or the parity bit, we can reconstruct the data for that byte and again construct that particular damage bit. So now we will construct this RAID level 1. Now we can see at this RAID level 2, there are 3 parity bits that is attached to the data store blocks of that particular disk. So if we compare this with RAID level 1, which needed as many of the data disk to store the mirroring, but here it is needed only 3 or 2 and more 3 bits of parity bits to compare it with this particular data disk. So it is comparatively better in terms of the number of disks involved in that particular RAID structure. The next level we will discuss is a RAID level 3. The RAID level 3 uses the bit interleaved parity bit checking. Now this RAID level 3 takes into account for the RAID level 2 that in fact that the memory system, unlike this, the disk controller uses the sectors to be interleaved to this parity organization, which gives us the idea other than that for this error correction also as for the detection of that particular sector. So here the idea is we first divide this disk on sectors and then store the bits on sectors of other disk. So like RAID level 2, we first stored in the disk 1 of this first sector the first bit, next on disk 2 the second sector of the first disk. So in this way we divide the sectors and can tell us that which bit is stored in that particular sector. So whenever a disk is damaged, so we can definitely say that which sector is damaged, so we can particularly repair that sector only other than replacing the whole disk. So it is better to use this RAID level 3 which have performance improvement over RAID level 2 because it uses a lesser parity bit only for the sectors, not for each bits of the each sector. So here only parity bit that is related to a corresponding sector will get changed if there is a bit damage on that particular block. So the sector will be then replaced or repaired on the performance basis. Now we will construct this RAID level 3. Here we can see for all the disk and sector there is only one parity bit for the sectors. So if any bits get damaged on say disk sectors of disk 1, so we can get the data from sectors of other disk to reconstruct the data using this parity bit or error coding checking. It has two advantages over this RAID level 1 as the first one is the number of disks required to store the data because it needs only one parity bit, whereas this level 1 is all the data stored disk as mirrored. And the second advantage is more important because we know that n-way striping of data for read and write access on that particular sector on disk is possible. So for accessing n plus 1 data disk reads, we can have an n-way striping of data which provides n times faster speed than it is accessing in read level 1, because now it can only have to read the 4 sectors of that particular data, not all the data that are stored inside this as well as this mirrored disk. But the configuration negative side is it has lesser IO, because every disk has to be performed its IO whenever there is a damage or request for repair. Other than this problem, RAID level 3 has some performance issue too, like for computing and then rewriting back these parity bits. As we know that whenever these disk sectors get changed, so the parity bits have to be updated and then it need to be reflected again associated with each sector. So this computation takes a huge time and also leaves us with a slower performance. So obviously this parity bit will be slower than any other non-parity bit scheme of RAID levels. So to impair this type of performance, we introduce a caching type of different. Now this caching department will handle by a hardware controller for every parity hardware on that bit. The hardware controller will then allow to write to the disks while the parity bits is modified in the hardware controller. So the writing can be executed concurrently while parity bits is modified. The parity bits is modified and after that it is written back to the system. In fact, it will be outperform the use of the non-parity non-caching bits for a caching with parity bit scheme. Now we will move to our next RAID level. The next level is a RAID level 4. RAID level 4 is a block interleaved parity organization. Like this RAID level 3, which was an bit interleaved parity organization, there was every parity bit in that sector for associated with the sector of the disk with a bit. Now we are using the striping in case of the blocks, not the bits. So the block level striping is used in this RAID level 4. Here we can say that the parity bit is associated with every block rather than in every sector within that disk. So if a block gets damaged on a particular disk, then the other corresponding sectors of that disk that can be repaired on that particular block which get damaged. So it uses the same RAID level 3 architecture with another enhancement that the block now can be repaired other than repairing every sectors in that particular block. So now the read access on this particular RAID becomes simple and easy, while other disks can perform other requests as well. The rate of this high data transfer because it supports multiple disk read access from this block. See, if the blocks are separated over the disk, so we can write to a block or read to a block while other reads are performed on another blocks by this disk performers. So the disk controller will allow this multiple reads to be accessed at once. Now multiple writes also can be accessed at once in these disks, which will make this parity bit changing very easier. But the smaller amount of writes, that is smaller than the amount of a block, so cannot be write by simultaneously. Say a block contains two partitions, one write is being modified and another is not modified. So it needs that the data should be first read, then it modified on this device controller, and then the modification to be written back to this particular disk block. So we need two of these accesses, first the read and first the read. Next, for the read and write, after that every read and write will correspond to the parity bit modification, and the parity bits also get modified to read and write. This include a read, modify, write cycles. For this type of cycles, we need two reads and two writes for each block. That is one read and write for configuring the actual writes in the block, another read and write for the parity bits to get modified. So this RAID levels 4 is implemented in generally waffle system, which is used by most of the operating systems. Here the RAID level should be implemented seamlessly, and every block that is containing zeros bits, so the parity bit will be 0 and still be correct. So here we do not have to update the parity bits according to the need. That the RAID level 4 looks like just like RAID level 3 because it is also used 1 parity bits per blocks. So it is same like this RAID level 3. Now we will move to our next RAID level, that is RAID level 5. RAID level 5 uses block interleaved but distributed parity organization. It is almost same as block level 4, but the only enhancement is that now the blocks are interleaved because every block is associated with a parity rather than we are distributing the parity over the blocks. So if there is n plus 1 blocks, so the parity is distributed over this n plus 1 blocks other than storing all the data in the blocks and parity in other disk. So here the parity is combined with the data that is stored inside that particular disk or the block. So storing this type of distributed parity gives us the flexibility to choose between the disk and the parity. Say for if there is an 5 or the disk parity, then we can say that the parity bit for this disk 1 will be stored in disk 1 plus 5 mod 1 plus 5. So this disk 1 plus 5 mod 5 plus 1 will give then the disk 1's parity bit will be stored in disk 2, 2's parity bit will be stored in disk 3 and like this. So whenever we are storing the parity bit other than the disk, so it is known as distributed. Among it given us the feature that the parity bit will needed to get distributed and repaired of that particular disk. So say suppose a bit is get damaged on disk 1. So its parity bit is stored in disk 2. So generally the data will be not lost because the parity bit is already in the other disk. So the nth block of every disk is storing the n minus 1th disk block's parity bit. So using this parity bit and other bytes of that particular block, we can reconstruct the data and tell us that where the bits got damaged and repair it very seamlessly. So in RAID level 5, we have every parity bit associated with every disk that we can access. So it gives us an advantage and the crucial one than over this RAID level 4 that it uses block interleaved partitioning but uses every parity bit that the disk 1's parity bit is stored in disk 2, 2's parity bit in disk 3, 3's parity bit in disk 4. So it also notes that the parity bit get distributed as well as the parity will be restored as it is stored in the other disk. Now we will move to our next type of RAID level, that is RAID level 6. RAID level 6 implements P plus Q almost implementation. This P plus Q implementation uses just as well as RAID level 5 with some more redundant disks for information to guard against that particular data loss. Say if the data is lost during this of RAID level 5, so we can store it using the other disk for storing the parity bits as well as for storing the parity bits of this particular disk. So here we are storing the parity bits along with the disk of data, and other than this disk we are storing another 2 or 3 parity bit disk to get the disk access failure rate survival. So whenever this type of scheme is used, we can survive more than one disk failure at once. So if there is 2 more redundant information, then we can survive more than 2 number of disk failures at once. So here we can see that these 2 parity bits are stored along with this RAID level 5 architecture, which uses the disk along with the parity bits. So it is definitely has more reliability over RAID level 5, but it is not implemented because it reaches an overhead of that extra disk that is required for storing the redundant information. The last type of red label we will discuss is red level 1 plus 0 and red level 0 plus 1. In red level 0 plus 1 is essentially a combination of red level 0 and red level 1. As we know that red level 0 gives us the performance and red level 1 gives us the reliability. So any operating system which needs a combination of all this performance and reliability will then combine the features of this 0 and 1, which gives us a new level, red level 0 plus 1. In this red level 0 plus 1, we first stripe the disks over the blocks and then mirrors it to that other disk. So unfortunately it requires, like this red level 1, more or the number of disks exactly the data are stored for mirroring the disk. As well as it has some one disadvantage too. That disadvantage is if that one disk fails in the type of 0 plus 1, then we cannot access any of the disk stripes on that block levels because it is again mirrored to another level. So all the disk on this particular stripe is inaccessible, leaving only the mirror image possible. So first we will see that how is red level 0 plus 1 constructed. So here the features of 0 is implemented first, that is striping of the disk accesses, and then the features of 1 is used, that is mirroring of the data. Now if we can say that there is a single disk failure, say for this one X, so this particular stripe of will be inaccessible, thus leaving with only the mirror image on this one. So all the disk will become then wasted. So another type of implementation just by the combination of the 0 and 1 is there, that is in red level 1 plus 0. This 1 plus 0 implements in the same way, but first every disk get mirrored and then all these levels is get striped off. So here if there is any single disk failure, we can first use that particular mirrored image of that disk other than striping off all the disk that is being wasted. So other disk can be used as well as the mirrored disk of that particular damaged disk. So here the redundancy is much more greater than the 0 plus 1. So we will now construct red level 1 plus 0. So here we can see that first every disk image is get mirrored and then this mirroring of this image gets striped off. So the data are available across the disk and spread over this multiple disks, but the mirroring will then support if there is a single disk failure, then it will only disk fail of this particular one because its mirror image is available, but it will not affect the other disk as they are not striped off with itself. So they are striped off on the mirroring image and only this type of images is there. So that is all for the red level 0. Now we'll move to our next section, that is selecting a red level and implementing a red level. So there are many areas where we can implement this red level. So the first area we will implement this red level is in volume management software area. In this area, the red level is implemented in either the kernel or at the system software service areas. So we can say that where this kernel is used and this application of this parity bits in the kernel area will become slower. So that is why only red level 0, 1 or a combination of 1 plus 0 is used in that type of related software. The next is the host bus affection. The host bus affection or HBA controller directly implements these read levels only in the disk that is connected to directly via this HBA. This cost in lower, but it does not provide very improvement in this particular reliability. The next is the hardware of the storage area implementation. The hardware of this particular storage area in the main memory will give us allowing dividing the sectors into multiple volumes and then again slicing up this striping of data into smaller disk. And now it is represented to the operating system. Now the operating system can perform this RAID level implementation at various levels of this, like RAID level 0, 1, 3, 5 can be implemented in this type of area. So the RAID levels can be implemented at each of this client or server, or then it can be implemented in the storage area network, where which can take advantage of multiple hosts of this arrays features as well as the RAID level implementation. Another area where we can implement this RAID level is that SAN or storage area network. To provide the storage area network, the RAID level is implemented between the client and the server, or say two hosts. So we can access the data between this host and server. First, the server gets request from the client and this RAID level is implemented like striping of this disk, and then this RAID level is again implemented on the client side when the server sends the requested data back to the client. So here we need two levels of implementation, one in the client side and another is the server side. The other side of this RAID level implementation includes the snapshot and replication. Snapshots gives us a full copy of that previous old data, that is the disk, before any updation or this last modification was made to it. So the snapshot now gives us that providing RAID level 0 and RAID level 1, that gives us the mirroring of that particular data image, that is copying the data disk onto the particular data beforehand of any updation, so that we can get back to the data which was being automatically updated. The replication stands for duplication of this data automatically when the disk gets failed or any single block on that disk get damaged. So the replication can of these two types. One is synchronous, another is asynchronous. A synchronous application, both the client and server side has to be confirmed that the writes made to any types of data that is being done on the server side as well as the client side. So the RAID level 3 can be implemented in this type of area. The asynchronous of this replication supports that the writes can be done in group. So the writes on the server side can be done, then place it in a buffer, and then periodically it writes it back to the client side. So there can be performed any type of data that is lost during this asynchronous translation. So here we can perform this RAID level 4 and 5, which uses the block interleaved parity and block interleaved distributed parity of the organization. Now the implementation of RAID levels differs on the system that is used by this implementation. Say for an example, if the RAID levels are implemented at the software level, then the software itself has to manage the data that is being accessed. The striping of the mirroring can be done only at that particular host that is using the particular software. But if RAID levels is implemented at the interconnect band or the SAN, then the host features can use any types of the operating system. It can be used all these RAID levels of implementation. So the RAID levels implemented in the SAN is more efficient than it is implemented in the software in terms of this high transfer data rate as well as the disk overhead of storing the data. Now another type of implementation of RAID level is in hot spare disk or disks. A hot spare is a disk that is kept along with this other disk of data storing that is used for this rebuild of that configuration of data. Here this hot spare disk can rebuild automatically that RAID structure within that implementation without any intervention of the human. So the failed disk will be reconfigured automatically, other than the disk should be replaced by the human. So if there is more than one hot spare disk, then the disk that is suffers from failure can survive more than one time. Now we will move to our last section, that is selecting the levels of implementation on this RAID. So given with many choices, the system designers must select very wisely that which RAID level to implement at which operating system. So the cost important in this factor is that the reliability as well as performance. So when we are talking about an high performance and the data needs to be continuously supplied to that software, so the RAID levels to be implemented very wisely and crucially. Say for an example, when we are choosing the RAID level 0, then we are considering that data loss is not that much crucial. And when we are considering the RAID level 1, then we are considering that reliability is very expensive as well as the cost is not a factor. But choosing a combination of 0 plus 1 or 1 plus 0 RAID level will give us that a combination of performance as well as reliability, which is implemented in many of the operating systems. Now RAID level 5 is always chosen over RAID level 6 because the 6 suffers most overhead problem contention for this disk on. But it has efficiency more than RAID level 5. Now the rebuild consideration is varies from this RAID levels. Say for this one RAID level, the rebuild is very easy, that we need to just copy the data from one disk to another disk as all the disk has been already mirrored. But the rebuild time for RAID level 5 is much more than RAID level 1 because it takes that every disk levels that is associated with it need to get copied again. So the parity bits also attached with its disk data blocks needs to get copied. So RAID level 5 is considered a less efficient when the consideration factor is rebuildation. Now along with this RAID level 5, 1 and 0, there are some other factors which need to be taken care of while we are configuring this RAID level implementation. The first question is how many disks are required for disk replacement or implementation of the RAID levels. And the second one is how many bits are associated with each parity bit. If we are implementing high number of disks in that particular RAID level implementation, then it will definitely greater the data transfer rate. Because higher the number of data transfer rate, higher the disks are there. But it also makes the system very expensive as the disks are needed while magnetic disk is very expensive. Now if you consider the factor that the number of bits that is associated with each parity bit. If the number of bits that is associated with each parity bit is higher, then we can consider that it will cost a less disk because the parity bits are now considering with a less disk space. But if such in a case that the second disk failure occurs before the first disk gets repaired by this parity bit and written back, then this type of the disk failure will suffer from data loss if the higher number of disks are attached with one parity bit. So that are the factors we should keep in mind while selecting this level of implementation by RAID into particular system. The types of the system, the nature of the system, as well as what type of access is made to the system, all should be taken care while we are choosing a particular RAID level implementation. That is all for RAID levels today. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.